All right, welcome back. We're going to continue on with our lessons in dynamics. And so what we're looking at today is something called free body diagrams. Whenever we solve problems in physics, it's really important that we have everything, all of our information laid out in a way that's going to help us be successful with that. And one of the most important things we can do when we're talking about forces is to draw a diagram that's going to tell us both where the forces are, which way they're pointing, and also how big they are in the direction that they're moving. So we use something called a free body diagram called an FBD to do that. And in order to do that, we're going to use a lot of the same forces over and over again. So we're just going to make a list here of some of the most common forces that are going to come up, and then we'll have those ready to go. So an example of a force that we already know, we've already learned about, is Fg. And of course that is just good old gravity. And as we discussed in the previous video, gravity is a force in our universe that pulls all objects together. All matter exerts this force across whatever distance. The next force we're going to include here, I'm just going to call this Fa. And Fa is the applied force. So the applied force is really kind of a bit of a cheat because we say that it is any push or pull. And so anytime that we have a force acting on an object and we're not quite sure what to call it, we might call it an applied force. You could think of the force of the car engine exerting on the tires so that it moves forwards, or you pushing your friend as they walk down the hallway, or you throwing a ball. All of these are just applied forces as a bit of a catch-all. The next one that we'll talk about here is normal force, so Fn. Fn stands for normal force, and the normal force is it's a supporting force. So anytime a structure holds something up, for example, I'm sitting in a chair, there's a normal force pushing on me so I don't fall and hit the ground. If you're walking along the floor must be supporting you, otherwise you would fall through it. One thing to keep in mind with a normal force is that it is always it always acts perpendicular to the surface that we're talking about. So we often think of normal force as being up, but it's not always if the surface is in a different, is not horizontal. So if you're not familiar with that symbol there, looks like an upside down T, that's just a symbol for perpendicular. We got parallel and perpendicular. And so that's the way our normal force is going to work. And then another one we'll see a lot of is FF. And that, of course, is our dear friend friction. Now, friction does come in a few different varieties, and in physics 11 land, we typically think about sliding friction. So that's the force that kind of tries to prevent objects from sliding past each other. So it prevents sliding. Okay, so anytime you can imagine if you hit the brakes on your bike and you skid to a stop, there's a lot of friction between the tire and the ground, slowing you down, bringing you to a stop. Our next force that we're going to look at, that we're going to talk a fair bit about, is tension force. So Ft is tension. And tension is like an internal force that acts along a string or a chain or a rope or anything of that nature. So we'll just call it force along a rope. But it could be anything really. Could contain tension. It's similar to, but slightly different from the next one, which is our spring force. So Fs is spring force. And spring force happens whenever something changes shape. So as you think of a rope, when you pull on it, it doesn't really stretch out, but an elastic band would, or a spring, or a bungee cord. So when those things change their shape, they tend to want to snap back into position. So we would call this a restoring force. And that can be on anything that you've changed the shape of, a bouncy ball or whatever. And last but not least, we're going to include here F air. Okay, and we often ignore air resistance. It's kind of a bit of a running joke in introductory physics that we just assume that it's negligible. But air resistance is important sometimes. I will say that for virtually all the problems we're going to do in this course, unless we say otherwise, you can assume that air resistance is negligible and it isn't going to be a big deal. So what we're going to do with these forces, when we have a situation, we're going to model it with a free body diagram. Now the great news is that in order to draw these diagrams, you have to have the same artistic ability, or better, as what I have. And I am able to draw boxes and arrows. So if you can match that, then congratulations, you too can draw free body diagrams. Let's look at this first example I've got here. A box is pushed across a rough floor at a constant velocity. So what I'm going to do is I'm going to draw all the forces acting on that box. And I'm going to do it in a way where typically the forces are going to start from the center of mass and come downwards. Like one force that I would include here would be the force of gravity. I'm assuming this box and this floor are on Earth, and so there's a force of gravity pulling straight down. Now that box doesn't fall through the floor, so there must be a force upwards or a normal force, a supporting force, preventing it from falling through the floor. Now when we think about these two forces, gravity pulling down, normal force pushing up, not only does the direction matter, but so does the size. So the length of the arrow is going to correspond to the amount of force. And these two forces are balanced. So I'm going to put a little hash mark there to kind of note that they must be canceling each other out because we're not accelerating up or down. Now it says we're pushing this box across a rough floor at a constant velocity. So since we're pushing the box, there must be an applied force. And I'm just going to say that the box is being pushed to the right. So I'm just going to make a little applied force here. Call that FA, pushing it to the right. And it's a rough floor, so it makes sense to me that there would probably be some friction as well. And friction would be back and to the left. And let's think about how big this friction force should be. It's tempting to draw a friction force that is smaller than the applied force. But in this case, actually, those forces would be the same. So the friction force is the same size as the applied force. Now, why is that? I thought this box was moving. The key here is that the box is moving at a constant velocity. So if the box is moving along at a constant velocity, then the forces, the net force on it must be zero. All of the forces must cancel out. There is no acceleration. Now you look at that picture and it doesn't really look like it's moving. And that's an important thing to recognize about free body diagrams, is that we can't actually tell that much about the velocity. What we can tell from the diagram is the acceleration. So I can look at this picture and see that the box is moving at a constant velocity, but that could be a constant velocity of 10 meters per second or 10,000 meters per second. I can't tell from the picture. But I can tell everything about the acceleration and nothing about the velocity. So let's try another example here. So a hockey player glides on frictionless ice at a constant velocity. Well, most hockey players I've ever seen have been on Earth. And so again, there's probably a force of gravity pulling down on them and a normal force supporting them. And again, those two forces would be equal and opposite. You don't have to draw these little hash marks, but I like to when I want to make it clear. If you draw them to be like approximately the same length, we will presume that they are. And so the hockey player is gliding. Let's assume they're gliding to the right on this ice. And of course, it's physics 11 land, so there's no friction. But it'd be really tempting to come along here and add an applied force. Well, if there's no friction, but there is an applied force, then that hockey player must be accelerating. And so that can't be the case because we're moving here at a constant velocity. So oddly enough, there is no applied force because you don't need any force to keep going at a constant velocity if there's no force pulling back on you. So in actual fact, that free body diagram right there is complete. So there's a whole bunch of examples here, and some are pretty simple and some are maybe a little bit more thinking involved. And we're going to use this exact same idea when we draw our free body diagrams, and it's really good practice. I would recommend hitting pause on the video and just trying a few and then unpause and so on, just to kind of see how it goes. It's definitely much better if you try it on your own first. So, first things first, a book sits at rest on a tabletop. Okay, well, that was pretty difficult. There's a book, and this book is probably on Earth, so I'm going to draw a force of gravity, and it's sitting on the tabletop doing nothing in particular, so I'm going to have a normal force upwards of the same size. Okay, so far so good. Okay, a girl sleeps in a hammock which is attached to the ceiling by 2 ropes. This is going to require a little bit more artistic ability, so let's see if I get this right here. And yes, that's a girl in a hammock. Perfect, nailed it. She is subject to the laws of the universe, meaning there is a weight pulling down on her. But she's being attached, the hammock itself is attached to the ceiling by 2 ropes. So that would be a tension force, but really not one tension force, but 2. And you can imagine that since there are 2 tension forces upwards, each of those individual tension forces must be smaller than the force of gravity downwards. Those 2 tension forces would add up to her 1 force of gravity pulling down. If both of those tension forces were the same size as gravity, there would be a net force upwards. And that's not a hammock, that's a slingshot. And people don't go in those, so that doesn't make sense. If I have an egg falling from a tree, there's an egg falling from a tree. And if it is free falling from the tree, it says here neglect air resistance, because of course I'm going to. I've got a force of gravity pulling down, and that's it. There's no other forces exerting on it. It's free falling. And this really is the definition of free fall, when there's only gravity pulling on you. Let's see, we got a plane flying at a constant velocity. So, okay, and nailed it. Now this plane is flying at a constant velocity, and it gives us a little hint here. It says there's an applied force forwards, okay, great, and there's a lift force provided by the wings. So there's like some new kind of force here that I haven't encountered, but that's okay. I'm going to add an applied force here. Okay, I got a nice applied force like that. And it told me that I've also got a lift force. So the way that aerodynamics works, we create lift on a plane's wings by moving through the air. So I've got these two forces in place, and I don't know too much about their relative size. I'm just going to draw them like that. But since this plane is flying, let's say, forwards and not falling out of the air, the lift force must be just equal to the force of gravity. Those two must be canceling each other out. And again, we're flying at a constant velocity. So there must be something backwards, and that something backwards is air resistance. So there's an air resistance force backwards that is perfectly matching my applied force forwards. All right, so now I've got a book on a table being accelerated forwards, and so again, I've got an applied force here, I've got a force of gravity there, I've got a normal force there. Now my normal force and my force of gravity, those are going to equal each other because I'm just sliding and accelerating to the right. But since we're accelerating, there is a friction force, but the friction force would be smaller than the applied force. So there is a total net force going to the right, and that explains the acceleration. Let's see, and now we have a book being pushed across the table at a constant velocity. Okay, well, again, I've got a book, and this book has gravity. Always take the easy forces first, gravity and normal force. And there's an applied force. Now, we're now moving at a constant velocity, so I don't know, maybe we're tired from all this book pushing. What a difficult task that is. So maybe the applied force is smaller, and in fact, the applied force is so much smaller that it's just barely equal to friction. Now, in this case, the applied force is enough to keep moving, right? Compare this to our previous example. If you want to start the book moving, you need to give it a little extra push. But if you just want to keep the book moving, then you can push with an applied force that matches friction. They'd be the same in this case, just to keep it going at that constant velocity. All right, student with a backpack on their shoulder. So we've got a backpack, backpacks have mass, backpacks are on Earth, we've got gravity, and then it's being supported by one strap. I guess we might call that a tension force, and again, those two would be equal. And now we've got a skydiver falling with a constant velocity. So I'm not sure if you discussed this before, but if you jump out of a plane for whatever reason, you're gonna have some gravity pulling down on you. And that's not a big surprise. But what might be a surprise is that as you fall, the faster you fall, the faster you're moving, the more and more air is pushing against you. And in fact, this skydiver is now falling at a constant velocity. This is not free fall. The only reason that would happen is there must be a force upwards pushing against you. And this upwards force would be air resistance. So the faster you move, the stronger the air resistance is. And then eventually you can't speed up anymore. You've reached what's called terminal velocity. Now I just want to compare that example number 8 all the way back to example 1. If you notice, I mean, the forces themselves are different, air resistance and normal force, but if you look at the free body diagram, they look the same. And this is a textbook doing a very boring thing of sitting on a table, and this is a human that is falling through the air at hundreds of meters per second, and yet their free body diagrams look the same. So the message before, the key idea there is, the free body diagram tells us everything about the acceleration and nothing about the velocity. Both of those situations have no acceleration, but the skydiver obviously is moving much more quickly. Let's think about this, a football being kicked up in the air. So this football has already been kicked. It's left the punter's foot and it's flying up in the air. And because it's moving on Earth, then there is a force of gravity down. Now it'd be really tempting to add an applied force upwards. And I will say that while the ball is in contact with the kicker's foot, there would be an applied force. But after it's left the foot, the ball doesn't like remember being kicked. There's nothing pushing it upwards. Now the ball is still going upwards, but it's only going upwards because it has inertia. It was given velocity in the upwards direction. So in actual fact, this free body diagram is done. And make a note that number 9 is actually the exact same as number 3. So an egg falling down, a ball going up, have the same free body diagram because they're both accelerating downwards, even though they're moving in different ways. Okay, last but not least, I've got a car that is driving to the right and slowing down. So it's kind of like just coasting to the right. So I got a force of gravity pulling down, and I've got a normal force upwards. And because there's maybe some friction, some resistance to rolling, there's a friction force there. But there is no applied force forwards because you take your foot off the gas, you're just coasting, you're coasting to a stop. The car is moving forwards, but it's not being pushed forwards anymore. So this is the complete free body diagram there. All right, that is it for your notes on free body diagrams.